consider two loops like this. Obviously, as you can see, one is a circular loop, the other is a square loop. So basically, it's a small square loop of side, let it be A, at the center of a circular loop of, let's say, radius R. And it is given to you that A is very small compared to R. Okay. You have to derive their mutual inductance. The circular loop and the square loop are both in the same plane, the plane of your screen. Okay. So think about it and tell me in which of these loops you'll assume the current to be flowing and how you'll find out the flux in the other loop. In which loop will you assume the current to be flowing? See, these are the factors that you need to consider. Suppose you assume current to be flowing in one of them. What you have to think is, due to that current, okay, due to the chosen coil's current, do we know the expression for magnetic field at every point of the other coil? That's one thing. Why do you need to know magnetic field at every point of the other coil? Because you should calculate flux in the other coil. Okay. So see, even if you know the expression for magnetic field, sometimes calculating flux may be too tedious. Okay. So can we calculate flux in the other coil easily? If you can do that, then you can proceed. Okay. So that way you think. Isha, which coil or which loop will you assume the current to be flowing in? Rishi, what about you? Which loop will you assume the current to be flowing in?
The bigger loop.
Why?
Hmm.
Okay, listen, both of you. We have two choices here. We can assume current to be flowing in the circular loop and try to find out flux in the square loop. Or we can assume current to be flowing in the square loop and try to find out current in the flux in the circular loop. Let's say you assume current to be flowing in the circular loop. Let's call this as I1. Now the square loop is near the center of the circular loop. Okay. Do we know the expression for magnetic field produced at the center of a circular loop? Magnetic field at the center of a circular current carrying coil or current carrying loop. Have we ever derived it? Okay, fine. So see, we know the magnetic field at the center of a circular loop. it is mu naught I divided by 2r, where r is the radius of the circular loop. We even know magnetic field on the axis of a circular loop. Okay. But see, the square is not a single point. It consists a number of points, right? We know the formula only for magnetic field at the center of a circular loop. We don't know magnetic field away from the center. Okay. But there are some points in the square which are away from the center of the circular loop. But there is one thing we can take advantage of in this case. The size of the square is very small. Okay. So all points of the square are very close to the center of the circle. So you can assume, okay, that the magnetic field all over the square is uniform. Did you all understand what I just said?
So can you explain just one?
Due to a circular loop, we know the expression for magnetic field at its center. That is mu naught I by 2r. Okay. But at points away from the center, I'll expand this square just to explain. Yeah, I'll mark one point in green. At that point, we know the magnetic field. But at other points, these other points are away from the center of the circular loop, right? We don't know the magnetic field at these points. Okay. And if you don't know the magnetic field at those points, you cannot calculate flux through the square. Yes or no?
Yes, sir.
Then it won't serve the purpose. We should be able to calculate flux. Okay. But one thing we can take advantage of here is that the square given to you in the problem is a very small square. Compared to the size of the circle, the square is very small. And because the square is very small, even at other points of the square, okay, these yellow points that I'm marking, even at other points of the square, the field will almost be equal to that at the center of the circle. A slight variation will be there, but it's negligible. Okay. So what it means is we know the expression for magnetic field all over the square. Okay. Is this point clear to both of you? Isha, did you understand?
Yes, sir.
Rishi?
Yes, sir.
Okay. Okay. So if you take current in the circular loop, you will be able to calculate flux through the square loop because we know the field all over the square. It will be almost equal to that at the center. Slight variation will be there, we can ignore. Okay, this way we can solve this problem. Let us see what would have happened had we taken current in the square loop. I'll copy the diagram. If you assume current flowing in the square loop, let's say some current I. One of you tell me, what do we know about the magnetic field produced by a square loop? Or can you express the magnetic field produced by a square loop at any point based on the laws and mathematics that you know? Can you express the magnetic field produced by a square loop at any point? Yeah, you all need to revise. Square loop is a collection of 4 straight lines. Okay, and we know how to find out the magnetic field produced by a straight wire. Fine. But at the center of the square, if you see, it's quite easy to express the magnetic field. From all sides, it's at the same distance. You find out magnetic field produced by one side. Into 4 you do, you'll get magnetic field produced by all sides of the square. That's fine. But at points away from the center of the square, it becomes too complicated. From point to point, the field expression will become very complicated. For example, if you take a random point somewhere here, say this one. From one line, it is at one distance. From another line, it is at another distance. Third line, some other distance. Fourth line, some other distance. Okay, so it becomes difficult to express the magnetic field at each point, and we don't know the expression for it. Okay, so if you take current to be flowing in the square loop, it's very difficult. In fact, like for the level of mathematics that we have, it's impossible to express the magnetic field at these points of the circular loop. So we won't be able to calculate flux in the circular loop. It will produce, but we won't be able to calculate it. Okay, because there are some points inside the square loop, there are some points outside the square loop. All of them fall within the circular loop. All of them will contribute to flux, and we won't be able to calculate that. Okay, so by taking current in the square loop, it won't be possible to calculate flux in the circular loop and get mutual inductance. So we have to proceed this way. Take current in the circular loop, find out field in the square loop, flux in the square loop, divide them, you will get mutual inductance. So do this, both of you. You have to use this result. Magnetic field at the center of a circular loop is mu naught I by 2r. Okay. By making use of that, you can find out the mutual inductance in this case. Solve this question. Square side is given as A. It's a small square. Circle radius is given as R. Or, okay, let me ask one. Rishi, you tell. We know the magnetic field at the center of the circle. Current in the circle is I. So you can say magnetic field is mu naught I. Okay, current in the circle is I1. Mu naught I1 by 2R is the magnetic field. So Rishi, tell me, what is the flux produced in the square loop due to this magnetic field or by this magnetic field? How is magnetic flux calculated? Isha, can you tell how is magnetic flux calculated?
Well,
So integral.
Okay, Rishi, yeah, tell.
magnetic field
Hmm.
into area and
Okay, field dot
and
area vector. Yeah, continue.
and cos theta.
Okay, the dot product will be BA cos theta. And Isha was telling the integral formula. Yeah, if the magnetic field is non-uniform or the area vector is difficult to express, okay, then you'll have to use integral B dot dA. In this case, that is not necessary. You can use B dot A because the magnetic field at points of the square is almost uniform. Okay, it's almost same everywhere. Okay, so you can use B dot A. So let's apply this. Magnetic field is mu naught I by mu naught I1 by 2R. Rishi, how much is the area in which you are calculating the flux?
Area of the square is
Okay, area of
sir,
a
1 second.
square is A square.
Yeah, a square.
Is the same field present over the entire area?
Yes, sir.
Yes. Okay. Next, you can see the current flowing in the circular loop. Tell me, what is the direction of magnetic field it produces at the center? Because we need the angle between magnetic field and area vectors. So what is the direction of magnetic field produced by the circle at its center? Isha, what is the direction of magnetic field?
Into the screen.
Into the screen. See, Rishi, you just have to curl your right hand fingers along the flow of current. Current is flowing clockwise. Curl your right hand fingers clockwise. For me, this is into the screen. Okay. So magnetic field is into the screen. That is, it's in the Z direction, you can say, or perpendicular to the screen, you say. Now the square is in the plane of your screen. If the square is in the plane of your screen, then its area vector will be perpendicular to the screen. So magnetic field is perpendicular to the screen and area vector is also perpendicular to the screen. Then theta becomes 0, cos theta becomes 1. Okay, so we got the flux in the square loop due to current in the circular loop. And if you divide them, what does it become? Mu naught A square by 2R. This becomes their mutual inductance. Is this clear? Any doubt in this? Okay. Let's consider another system. First, any of you tell me, what is the magnetic field produced by a finite straight current carrying wire at a perpendicular distance of x from it? Assume these angles theta 1, theta 2 are known to you. Let's say there's a current I flowing. What is the expression for magnetic field at that point? Okay.
Sir,
Huh.
can you repeat the question once again?
What is the formula for magnetic field produced by a straight wire at a distance x from the wire?
Mu naught I by 4 pi r into sine theta 1 plus sine theta 2.
Okay. See, if you take angles at the ends of the wire, no, it is cos theta 1 plus cos theta 2.
Yes.
Okay. If you use these angles, okay, I'll call them as alpha 1 and alpha 2. In terms of these angles, it will be sine alpha 1 plus sine alpha 2. Okay. Right. So you know the magnetic field that one straight wire produces. If you know magnetic field that one straight wire produces, then you can tell or you can calculate the magnetic field that 4 wires would produce, which means you can find out the magnetic field at the center of a square. Okay. So try this question now. Suppose there is a square loop this time. Side A. At the center of the square loop, there is a circular loop. Very small circular loop, as you can see. Okay. Circular loop radius is R, and R is very small compared to A. Derive the mutual inductance between them.
Sir, 1 second, can you show the second case once?
The magnetic field formula. Okay.
Okay, sir, done.
Derive the mutual inductance between this square loop and the circular loop. What happened? Any answer? Okay. Rishi, tell me in which loop shall we assume the current?
Sir, the square loop.
Why? Okay. Isha, in which loop shall we assume the current?
Square.
How does it make it easy to solve?
So because the circle is very small, so the flux won't be that different in that.
The field won't change much
Yeah,
from point to
field.
point. Okay. Okay, fine. So same reason, same logic that we used before. If you assume current in the square, see, for a square is a set of 4 straight wires, square loop. We can easily find out what is the magnetic field at the center of the square. Okay. Now center of the square is just one point. That's not the entire area of the circle, because we need flux through the circle. But the other points of the circle also are quite close to the center of the square. So the magnetic field through the circle will almost be equal, like at every point will almost be equal to the magnetic field at the center. Because the circle's area itself is not much, the variation won't be significant. Okay. So magnetic field at the center of the square is equal to magnetic field at all points of the circle. So the circle experiences almost a uniform magnetic field due to current of the square. Had you taken the other way around, suppose you took current in the circular loop, you can't even write the expression for magnetic field out of a circle. For circle also, we know only at the center, away from the center of the circle, we don't know the expression for magnetic field. And if you don't know the expression for magnetic field, you can't calculate magnetic flux. Okay. So if you take current in the circular loop and try to express flux in the square loop, it's not possible. You won't be able to calculate mutual inductance. So this is the only way you can do for the formulas and mathematics that we know. Okay. So now we have to find out what is the magnetic field at the center of the square. That gives us the magnetic field in the circle. With that, we can find out flux in the circle and divide flux in the circle by current in the square. You'll get their mutual inductance. Okay. Did any of you derive magnetic field at the center of the square? Let's consider one wire of the square. So you need to stay in touch with all this. Okay. The distance from the wire to the center of the square will be half of the side. So x, in place of x, you will write a by 2. This angle will be 45 degrees. This angle will also be 45 degrees because it's a square. So theta 1, theta 2 are 45 degrees. Field due to one side of the square is mu naught I by 4 pi. In place of x, you will write a by 2 cos 45 degrees, that is cos theta 1 plus cos theta 2 is also cos 45 degrees. Cos 45, 1 by root 2 plus 1 by root 2 becomes root 2. So this becomes, okay, 2 gets cancelled. And this root 2, this 2, 1 root 2 will be left in the denominator. Mu naught I by root 2 pi a is the field due to one side of the square. Then field due to the all four sides, due to all the four sides of the square, will be 4 times of this. 4 into mu naught I by root 2 pi a becomes 2 root 2 mu naught I divided by pi a. That's the magnetic field produced by current in the square at its center. This itself will be the magnetic field at all points of the circle. Okay, we know the magnetic field now at all points of the circle. And in the square, let's assume the current is flowing clockwise, then magnetic field will be inwards. Circle's area vector will also be perpendicular to your screen. So angle between magnetic field and area is 0. Therefore, the flux in the circle, you can call it as flux in the second coil, is the magnetic field that exists in that region. multiplied with the area of the circle, pi r square. That's all. And if you want their mutual inductance, do phi 2 divided by I1. Just send I1 to this side. The answer is, okay, pi gets cancelled. 2 root 2 mu naught r square by A. That's the mutual inductance between the square loop and the circular loop. See, you all need to revise. I'll give you some more questions in the worksheet. You revise the formula for magnetic field produced by that system, you'll be able to easily calculate the mutual inductance. Okay. Let's consider one more case. Just a moment. I need a solenoid. Suppose there are two long solenoids. Okay, assume this is one. Let's say this is the other one. We'll color it differently. Just a moment. What color shall we take? Okay, green. Right. Assume the second one has a slightly smaller radius compared to the first one. And they are both having the same axis. They are coaxial. So this is the situation. They're of the same length, but their radii are different. Okay, maybe I should stretch the black one a little bit. I'll do that. Yeah, so the green one is inside the black one. Okay, not so much. Fine. So two coaxial solenoids. Let me draw their common axis. This is their common axis. Okay. The black one's radius, let it be R1, and assume it has N1 number of turns per unit length. For a solenoid, small n stands for number of turns per unit length. Okay. And let's say its total length is L. The other one is the green one. The green coil's radius, the green solenoid's radius, let's take it as R2. Assume it has, okay, I'll write it on that side itself. Green one's radius is R2. Number of turns per unit length is N2, but it has the same total length. Okay, both solenoids have the same length. So they are coaxial solenoids of equal length. Radii are different, number of turns per unit length are different. Okay. We have to derive their mutual inductance. So as usual, what we are going to do is we are going to assume current in one of them and find out flux in the other one and divide. Rishi, tell me, in which solenoid shall we assume the current? Outer one, the black one, or the inner one, green?
But the outer one only.
Okay, let us do it like that. Let's assume the outer coil carries a current I1. It's a solenoid. We know the expression for magnetic field produced by a solenoid inside it. Okay. Luckily, the second coil is completely inside the solenoid. We know the expression for magnetic field produced by long solenoid outside also. It is 0. Okay. But here, luckily, the entire second coil, the green one, is inside the first coil. So we know the magnetic field at every point of the second coil due to the current passing in the first coil. And if you know the magnetic field, then it's easy to express flux and calculate the mutual inductance. Let us do this. So Rishi, tell me, what is the formula for magnetic field produced by a long solenoid?
Sir, is it mu naught n by r square? Is it that one?
No.
Sir.
Magnetic field produced by a long solenoid carrying a current I. Okay, Isha, tell me the formula.
So mu naught Ni.
Mu naught Ni. Okay. Here, the number of turns per unit length of the black solenoid is N1. And the current passing in it is I1. So mu naught N1 I1 is the field that it produces inside. Outside it is 0. Everywhere inside the black solenoid, if the field is same, that means this same field exists at all points of the inner solenoid. So the inner solenoid, the green one, is under or is inside a uniform magnetic field. Okay. What is the direction of magnetic field produced by a solenoid? Anyone? What is the direction of the magnetic field produced by a solenoid?
Parallel to its axis.
Along the axis. Okay. In this case, current is flowing this way. So it will be to the left. The field produced by the black solenoid is this way. Okay. Now see, the inner solenoid, the green one, is a collection of circular loops. Actually, that much gap should not be shown, but for our understanding, we show so much gap between the turns of a solenoid. Usually the turns are very close to each other. Each turn is like a full circle. Okay. Now their axis is common. Okay. The axis of the solenoids is common. Means the turns of the inner solenoid and the turns of the outer solenoid are in the same plane, the plane perpendicular to your screen. So the area vector of any turn of the inner solenoid will also be along the axis itself. So magnetic field produced by the outer solenoid is along the axis, and the area vector of any turn of the inner solenoid is also along the axis. Then it means the angle between the magnetic field and area vector is 0. Then we can easily write down, we can easily express the flux in the second coil. Tell me this, all of you, both of you, what is the flux in each turn of inner solenoid? How much magnetic field passes through the inner solenoid? The magnetic field produced by the outer one, that is mu naught Ni, N1 I1. Okay. What is the area of each turn? Okay, each turn is a circle, as I said. What is the area of each of those circles of the inner solenoid?
Pi r square.
Correct. Which R? R1 or R2?
R1.
R1 is the radius of the outer solenoid. It is R2 square.
That's R.
Okay. We are expressing the flux in the inner solenoid. So inner solenoid's cross-sectional area we have to take by R2 square. That's the flux through each turn. Okay. How many total number of turns are there in the inner solenoid?
And
N2 is number of turns per unit length. So what is the total number of turns?
N by L.
N2 is total number per unit length. So total number in the second coil will be N2 into L. Number of turns per unit length multiplied with the length will give you the total number of turns. Okay. Flux through each turn of the inner solenoid we expressed. Therefore, total flux in the inner solenoid can be written like this. Mu naught N1 I1 pi R2 square, that's the flux in one turn, multiplied with number of turns is N2L. That's all. We got flux in the second solenoid due to current of the first solenoid. Then we are in a position to express mutual inductance. So mutual inductance between or of 2 with respect to 1 is phi 2 divided by I1. So if you divide by I1, this I1 gets removed from the equation. And what will you be left with? Mu naught N1 N2 L pi R2 square. That's the mutual inductance between these two solenoids. But we derived this by considering current in the outer solenoid and flux in the inner solenoid. Okay. Let us now do it the other way. We'll assume current flows in the inner solenoid and we'll find out how much flux it produces in the outer solenoid. Here the solenoids not getting selected. Okay. Again, same system, coaxial solenoids. Black one's radius is still R1. Number of turns per unit length is N1. Total length is L. Green one's radius is still R2. Number of turns per unit length L2. Total length L. This time we are going to assume current to be passing in the green one. So let's take it as I2, current in the second coil. It's also a solenoid. It's also a long solenoid. And long solenoid produces magnetic field along its axis. And outside a long solenoid, the field is 0. So the field anywhere inside the green solenoid will be this way. And outside the green solenoid, the field is 0. Okay. And this field, the field produced by the second solenoid, will be mu naught N2 I2. Mu naught Ni, we have to use N and I of that loop, that coil. Okay. Due to this magnetic field, we need to find out flux in the bigger solenoid. Now visualize cross section of the bigger solenoid. It will be circular in shape. Cross section means side view. When you look from the side, it look like a circle. Okay, it's like seeing a spring from one side. You only see the circular part. Its radius is R2. Oh, sorry, bigger one's radius was R1. Okay. Inside this, that smaller solenoid is there. That smaller solenoid's cross section also will be visible. And that smaller solenoid, what it is doing, it is producing field only in this region, inside itself. A solenoid, long solenoid, does not produce magnetic field outside itself. So this is what is happening. Its radius, okay, that inner solenoid's radius is R2. And we know this magnetic field. B is equal to mu naught N2 I2. Now we need flux in the bigger solenoid due to field produced by the smaller solenoid. Flux in each turn of outer solenoid is what we'll have to find out now. Now flux is magnetic field into area, that's fine. But tell me, does the entire outer solenoid's cross section have the same magnetic field?
No, sir.
No. In some part of the cross section, we know there is magnetic field. In the other part of the cross section, the magnetic field is 0. Okay, so in one part it is non-zero, in another part it is 0. So if you want total flux, what you have to do is you have to do this magnetic field that is there, field produced by the second loop, that field multiplied with the area over which that field extends plus the other field, which is 0, multiplied with the area over which the other field extends, remaining area. This is how you calculate magnetic field if one field exists in one part of the area and another field exists in another part of the area. Had there been the same field throughout the area, field into total area you can do. But here we are doing like suppose in one part the field is B1, area is A1. In another part the field is B2, area is A2. Then we are doing B1 A1 plus B2 A2. Is this step clear to both of you? Any doubt in this? Isha, did you understand?
Yes, sir.
Rishi, is it clear?
Yes, sir.
Okay. So this is the flux through each turn of the bigger solenoid. This term becomes 0. Leave it. B2 is mu naught N2 I2 and area is pi R2 square. Correct. Now what we need is the total flux in the outer solenoid. We know the flux through each turn. What is the total number of turns of the outer solenoid? Like capital N1, how much will it be?
N1L.
N1L, number of turns per unit length multiplied with the length. Therefore, total flux in the outer solenoid will be flux in each turn multiplied with number of turns. You get the result as, okay, we got the flux, that's fine. Now we can express the mutual inductance. So this time it is, okay, I should have written phi1. Flux in the first coil due to current in the second coil. So this time we are getting phi1 divided by I2. You call that as M12. Mutual inductance of first coil with respect to the second coil. And that becomes mu naught N1 N2 L pi R2 square itself. Once again, you get pi R2 square only. It doesn't depend on the bigger solenoid's radius R1. And if you observe, this result is same as this one. First result was derived by assuming current in the outer solenoid and finding out flux in the inner solenoid and dividing them. That was M21. Second result was derived by assuming current in the inner solenoid, flux in the outer solenoid and dividing them. This is M12. And we see that in this case, what case is this? Two long solenoids of the same length, coaxial. In this case, we see that M21 is equal to M12. Means it does not matter in which coil you take the current and in which coil you calculate the flux. Okay. And this result is true not only for this case. In this case, it's easy to derive. So we have done this. It's there in NCERT also. This result is true for any pair of coils. Okay. So you can go back to the problems that we solved before this. Like this question. What did we do? We assumed current in the square loop. Why? Because we can find out the field at its center and find out flux in the circle. We can get mutual inductance. So we got mutual inductance of the circle with respect to square. Even if you do the reverse, you will get the same result. Okay, mathematically it is not possible for us to do it, but if you do it, you will get the same result. So the conclusion is that to derive mutual inductance between two coils, it does not matter. Okay, for the end result, it does not matter which coil you take current in and which coil you calculate the flux in. The choice is yours. Okay, whichever is mathematically easy, you will take that. Okay. So this is true in general, mutual inductance of two coils. It doesn't matter in which one you take the current and in which one you try to find out the flux. Okay. Can one of you tell me the factors on which mutual inductance depends? We had discussed this before. Factors on which mutual inductance depends.
Third, the geometry.
Yeah, it depends on the shapes of the coils. It depends on the arrangement also. We had done that in the last class. Long solenoid and a circular loop inside it. Okay. In this case, we got one mutual inductance. In this case, we got mutual inductance to be 0. Okay. So yeah, it depends on the arrangement of the coils. What else? Generally, what does
Sir,
inductance? And
it doesn't depend on the second year, whatever coils we choose. So the order doesn't matter.
you don't tell what it doesn't depend on. What does it depend on? What are the factors on which it depends?
Medium.
Medium. Okay. Mutual inductance depends on first geometry of the coils. So individual shapes of the coils, it depends on that. Then their relative arrangement. And the medium between the coils. Right. Suppose the coils, individual coils, have self-inductances L1 and L2. Okay. Then the mutual inductance between them can be expressed as K under root L1 L2. Okay. We are not going to actually do this in any case, but it can be done. K root L1 L2. And K is called the coupling constant between the coils. What do we mean by coupling constant? The flux produced by one coil, how much of it passes through the second coil? Okay, it's somewhat related to that. That is how mutual inductance works. No, current in one coil produces a field. So that field produces flux in the second coil. Okay, so all the flux in the first coil may not go through the second coil. So how much of flux produced by the first coil actually goes through the second coil? K depends on that. That's called the coupling constant between the coils. Let's go back to yesterday's problem. Say this one. Okay. There's a long solenoid and a circular loop is placed parallel to the axis of the solenoid. Now in this case, we got mutual inductance to be 0 and it makes sense. We assumed current to be flowing in the solenoid. The solenoid is producing flux, as you can see, field lines are there. None of those field lines are cutting through the second coil. None of those field lines result in any flux through the second coil. So their mutual inductance is 0. In this case, you can say the coupling constant will be 0. See, the solenoid has its own mutual inductance. You can call it L1. The circle will have its own mutual inductance. You can call that L2. Okay, those are not zeros. Solenoid mutual inductance, we derived mu naught n square L pi r square. Circle also will have mutual inductance of its own. But when these two are put together like this, the mutual inductance turns out to be 0. And we know the formula now, mutual inductance is K times root L1 L2. L1 is non-zero, L2 is non-zero, but mutual inductance is 0. That means the coupling constant between them is 0. And it makes sense. None of the flux produced by the first coil is passing through the second coil. Okay. So this value K that is there, the coupling constant between coils, it ranges from 0 to 1. 0 case we have seen in that example. Flux produced by first coil does not pass through the second coil at all. Then the coupling constant is 0. Okay. When is the coupling constant 1? That is a case of perfect coupling. That happens when all the flux produced by one coil also passes through the other coil. That's a case of perfect coupling, and in that case, K will be equal to 1. Okay. So remember, mutual inductance M depends on the geometry of the individual coils first of all. That means it depends on inductance of the individual coils. And then it depends on relative arrangement and the medium. So you can express the mutual inductance in terms of self-inductances. M is equal to K into L1 L2, under root L1 L2. Okay. Where K is called a coupling constant. It can range from 0 to 1 depending on how the coils are arranged. Okay. So did you all understand what is coupling constant, how mutual inductance is related to self-inductance and all? Any doubt in this? Okay, fine. So what all have we discussed today? How to find out mutual inductance in some cases. Square loop, circular coil, square and circular loops. One outside, one inside, we have done that. Then in one particular case of two coaxial solenoids of the same length, we proved that M21 is equal to M12. Okay, and that result is true in all cases. If you are given two coils or loops and you are asked to find out the mutual inductance between them, it doesn't matter which one you can consider the current in and in which one you calculate the flux. Okay, the ratio will be the same. Mathematically, whichever is easy, you will prefer to do that. And then we discuss the relation between mutual inductance and self-inductance between two coils. Okay, M is K root L1 L2, K is called coupling constant. Okay, fine. The next part of this chapter will be AC generator, that we'll discuss in the next class. AC generator, we can talk about transformer also. Okay, step up transformer, step down, that we'll discuss in the next class. So if you all have any doubts, you can ask.